Welcome back to Algebra. Today we're going to talk about normalizers in the context of the Silo theorem. So we're going to talk about normalizers because they will come up in the proofs of the second and third Silo theorems. So let's go ahead and define what is a normalizer. So let G be a group and let K be a subgroup. Then the normalizer of K in G is defined by, I'm going to write the normalizer in G of K is going to be those elements in G such that when I conjugate K by G, I get K back. Okay, so that is a normalizer. And some notes. Let me just say, first of all, that the normalizer is a subgroup of G. I will just mention that, well, first of all, you can see that if G is in the normalizer, then the conjugate of K by G is K. So the conjugate by G inverse, if you just multiply by G inverse on the left and by G on the right, then you see that the conjugate of by G inverse is again K. So if G is in the subgroup, G inverse is also in the normalizer. And if G and H, when you conjugate by G, you get K. When you conjugate by H, you get K. If you conjugate by G times H, you will also get K. So it is closed under inversion, under multiplication. The identity element is, of course, in the normalizer, so it is a subgroup. Second, notice that if the normalizer is all of G, then that means that for every G, this identity is true, and therefore it means that K itself is normal in G. So the normalizer is helpful to measure how far a group is from being normal. Great. Also notice that so K is normal in G if the normalizer is all of G, but also always K itself is normal in the normalizer. Because if I take my group to be the normalizer, then everything in the normalizer satisfies this equality, so K is normal in the normalizer. And last, in fact, the normalizer is the largest subgroup of G that contains K and K is normal in it. All right, so because we do have that K is always normal in the normalizer, and this is a subgroup of G, and it is the normalizer is the largest subgroup of G where K is normal in that subgroup. Okay, so those are things that if you want, you can prove as an exercise, but they are fairly clear. All right, so let me give you some examples. For example, let K be 3z modulo 6z inside z modulo 6, so that's my G. Then what is the normalizer inside of G of K? Those will be, again, every G in G, such that G, K, G inverse is all of K. But in this notation, what we have is, well, we're doing groups under addition, so we're looking for classes in Z modulo 6 such that G plus K plus minus G is equal to K. but because we have that everything commutes, that will be every single element in G in Z modulo 6. That happens for every, so again, this piece here is because G is commutative, and in fact, if G is abelian and K is a subgroup, then we will always have that the normalizer is all of G. Great. How about another example? So now let K, we don't want an abelian group, so let's do something non-abelian. 1, 2, 3 is going to be in S3, that's my group G. So what is now the normalizer of K? Now it will be every G in S3 such that G 1, 2, 3 G inverse gives me all of 1, 2, 3 back. Okay, but we know that this K, this subgroup, we've proved it to be normal. Since K is normal in G, then the normalizer, which is the largest subgroup of G where K is normal, has to be all of G. It is normal, so for every G, this is satisfied. So in either way, we've proved that since K is normal, the entire normalizer is just all of G, all of S3. Great. So, and again, now, as we said before, if K is normal in G, then the normalizer has to be all of G. Great. So now let's try to find another normalizer, but in a case where it is not a normal subgroup. So as a third example, let's take K now to be the subgroup generated by 1, 2 as a subgroup of S3. Now this subgroup we know is not normal in S3, so the normalizer cannot be all of S3. So suppose G is in the normalizer. That means that GK, G inverse is K. But K is, well, it is the identity or 1, 2. It's one or the other. So what happens in particular, that will happen when if the element in K is identity, this will always happen, that we get the identity, right? So if we have G, E, G inverse, that will be G, G inverse, that is identity. So that works, but if I also have to normalize, it has to fix, it has to send 1, 2 also to some element of K, then this, if it is, the possibilities are that is the identity or give me back 1, 2. If we have that G times 1, 2, G inverse gives me the identity, that means that if I multiply on the right by G, that G 1, 2 is G, and that gives me that 1, 2 is the identity, which is a contradiction, so that cannot happen. Or G1, 2, G inverse gives me back 1, 2, but that means that G1, 2 is 1, 2 times G, and if that is happening, then G commutes with 1, 2, and you can check that there is nothing that commutes with 1, 2 except the identity. For example, 1, 3, 1, 2, 1, 3 is 2, 3. So that tells you, for example, that 1, 3 is not in the normalizer of K. Similarly, 2, 3, 1, 2, 2, 3, that is 1, 3. and that tells you that 2, 3 is not in the normalizer, and 1, 2, 3 times 1, 2 times the inverse, which is 1, 3, 2, that gives me 2, 3, which gives me that 1, 2, 3 is not in the normalizer. So there is nothing in the normalizer except the identity and 1, 2. So the normalizer of K, which is 1, 2, 3, is just all of K. Okay. By the way, note also, I'm not sure if actually I said that at the beginning, that K is always contained in its own normalizer, right? Because well, any K, if K is in K, then that will be just K again. So that implies that little k is in the normalizer of K. All right, so we've computed then that the normalizer, this tells me that in S3, the normalizer of the subgroup generated by 1, 2 is just 1, 2, just the group itself. Okay, so now let me prove a lemma that is one of the things that we will use in the proof of the second Zillow theorem. Okay, so here's the lemma I want to show now. Let P be a P-Zillow subgroup of G for some prime P. And let X have order a power of P. Okay, so the order of X is some power of P. Then if X, Px inverse is P, i.e. if X is in the normalizer in G of P, then X is in P. Now note, we have just shown that P has to be in the normalizer of P, and this shows that in that case, the normalizer is contained in P, and therefore the normalizer of P is just P. Okay, so let's prove this lemma as follows. So suppose, as in the statement, that X, Px inverse is P, and thus X is in the normalizer in G of P, the normalizer. All right, and we're going to look at the coset generated by X in the quotient of the normalizer by P, where recall that that P is normal in the normalizer, so that is a group. And note that the order of that subgroup generated by the coset XP has to also have a power of an order that is a power of P, a power of P. I don't think the power is important, so I'm just going to write a power of P because X itself has order a power of P. So some power, the powers of this coset, the consecutive powers of this coset, xp to the m will be x to the m times p. And if the order of x itself is a power of p, the order of the coset will also be a power of p. Perhaps not the same power, but some power of p. Okay. Now we have the correspondence theorem. So this is a subgroup of a quotient by the correspondence theorem, I know what those look like. So let me do that. So by the correspondence theorem, there is some other subgroup containing P, a subgroup of the normalizer, such that H modulo P is the subgroup generated by that coset XP. Now, since the size of H will be the size of P times the size of that subgroup, or rather, if you want, how did I get this? I get that the size of the quotient is the size of the subgroup generated by this coset, and this itself is the size of H divided by the size of P, and therefore I get this identity. But this is a power of P, and this is a power of P, so this itself is a power of P, and therefore the size of H is a power of P, and we also know actually that P is contained in H from this, right? This over here tells me that P is contained in H is contained in G, and P is a P-silo. But a P-silo is maximal, right? A P-silo is as large, so this one has a power of P, order power of P, order power of P inside G, but the P-silos are maximal with being a P group in G, so anything else that is in between is either all of G or P. But this is just of order a power of P, so they have to be the same. Okay, so this can't be, this is a power of P. So if it was all of G, then G itself will also be P. In either case, P is equal to H. So by the maximality of a P silo, we get that P has to be all of H. Okay, so so now that tells me that H modulo P is trivial, but that was exactly the subgroup generated by this coset is also trivial, and therefore XP must be just the trivial coset, the identity element in coset, which is P, and that tells me that X is in P, which is what I wanted to prove. Okay, great. So now I'm going to prove one more lemma about conjugates. So let's explain first what I mean by these business of conjugates of a subgroup. So recall that we are going to prove, one of the Sylow theorems tells me that if P1 and P2 are P-Sylow subgroups, then P1 and P2 are conjugates. So there is some sigma in G. So if these are subgroups of G, then there is some sigma in G such that sigma P1 sigma inverse is P2. They're conjugates. So we are going to want to talk about conjugates of one given subgroup because sometimes I might want to start from one P-silo and then find all the P-silos by taking conjugates. I also want to know how many different conjugates are there in G of a given group. That will give me how many P-silo subgroups are there by counting, if I am able to say how many conjugates are there. So let me define first that notion let H and K be subgroups, then the H conjugates of K are, so all the subgroups are subgroups of the form H, K, H inverse for any H in H. So that set, so this subgroup, some K prime, let's say, that is a conjugate, and we sometimes we might restrict, so the conjugates are only conjugates but with just with parameter H. So this means that, so the H conjugates of K, I'm going to look at conjugates of K, but only when I conjugate by something that is in H. Sometimes we'll just do like the G conjugate, so all of the conjugates of K is all conjugates of K, and those are all the subgroups of the form GK, G inverse for any G in G. So the special case of this is the G conjugates of K, which gives me back all the conjugates of K, but sometimes I want to restrict to some set of conjugates, which is only given by conjugation by elements in H. So I can actually count how many K primes are there in the following result. So here is another lemma. Let H and K be subgroups. Then the number of H conjugates of K is given by the index in H of the intersection of the normalizer with H. Okay, so the normalizer of K is a subgroup of G, and then if I intersect that subgroup with H, I get a subgroup of H, and the index of that subgroup in H counts how many conjugates are there. So here's the proof. For the proof of this, I'm going to write a bijection. So H conjugates of K, they're going to be in bijection with the right cosets of that subgroup, the intersection of the normalizer with H, and the map is going to go as follows. So if I have a conjugate, any conjugate is going to look like H, K, H inverse, and that conjugate is going to go to the coset and K intersect H, the right coset by that H. So let's prove that, first of all, this is well-defined, injective, and surjective. So 1 or 0, if you want, this is well-defined. Is this well-defined? Why do I need to prove that it is well-defined? When I say an H conjugate of K, certainly is of this form, but there could have been a different H that gives me the same conjugate, and I want to make sure that I get the same right coset. So suppose that a conjugate is given in two different ways. So if I have the same conjugate but given by two different h's, so for h and h prime in h, I want to make sure that the cosets are the same on the right-hand side. Okay, so if so, notice that if I multiply on the left by h inverse, I get h inverse h prime K, and if I multiply on the right by H on this side, I'm going to get H prime inverse H, which is the same as you see that this is actually H inverse H prime K, H inverse H prime inverse. So this is telling me that actually this element, when I conjugate by this element, I get back K. So H inverse H prime is, on one hand, it normalizes K. When I conjugate, I get back K. So it is in the normalizer. And certainly, H and H prime are in H, so it is also in H. So it's in the intersection of the normalizer and H. And therefore, that implies, so if H inverse H prime is in the normalizer of H, that will imply that actually the right cosets, by the properties of right cosets that we know, this one and the right coset by the other element of H, H prime, are the same. And therefore, the map is well defined. One, let's prove that was part 0. Now let's prove that the map is injective. So now for the injectivity, suppose that I have two H's that map to the same coset. So the coset by H1 is the same as the coset by H2. Then again, by the property of cosets, if the two cosets are the same, then H2, H1 inverse will belong to the group we're doing cosets by. So this will belong to NGK intersect H. So it is in H, that I know, that much I know, but it is in the normalizer of K. And since it is in the normalizer, I get that if I conjugate by H2, H1 inverse, if I conjugate K by that element, I will get K back. But if I now just multiply on the left by H2 inverse and on the right by H2, so then what I get is that H2 inverse K H2 is actually the same as H1 inverse K H1. I've multiplied and on here, multiply by H2 inverse here, and then I get an H2 inverse here, multiply by H2 over here, and I get an H2 here, and what remains is just H1 inverse K H1. So those two cosets, those two conjugates are the same, and therefore they are actually the same conjugates of K, and that tells me that the map came from the same conjugate, so the map is injective. Okay, and then let's prove that the map is surjective. What is the map? Remember that the map went from H conjugates of K to right cosets of the intersection of the normalizer and H. Right cosets where? Not in G, but in H. Okay. So, and the map goes from HK, from that conjugate of K, it was sent to NGK intersect H times H. So now it's clear that this is surjective. It is surjective because any conjugate, any coset of this is, well, it is exactly this times H for some H in H. Any coset of this in H is one of those, and thus, if I call this psi, psi of the conjugate by H will map precisely to that coset, and I get surjectivity. Okay. So that proves that it's surjective and concludes the proof of my lemma. Now, what have I just proved? We have proved, this is the statement, if H and K are subgroups of G, then the number of H conjugates of K is given by the index of the intersection of the normalizer in H. Okay, so as a corollary for our case, so let P be a P silo of G, then the number of conjugates of P in G is given by, well, what is H here um, is G, and I'm conjugating by things in G, and then the formula tells me that it will be the index of the normalizer of P intersect with G. But of course, the normalizer is a subgroup of G, so the intersection with G is just the normalizer itself. So it's the index of the normalizer of in G. So we will use this formula later in the next video to prove the Silo theorems. Okay, so and I'll stop here for today.